Institute of Aeronautical Engineering Autonomous. This is my TED talk. My name is N. Venkat Sai, rule number 23951802226. Subject HVDC transmissions. Subject code AEED28. My topic is HVDC system control, individual phase control, and equivalent firing control. Covers the two basic firing schemes used in HVDC converters, IPC and EPC. Department Electrical and Electronics Engineering. HVDC system control, individual phase versus equidistant firing. Delving into the fundamental firing schemes that govern high voltage direct current HVDC converter operations, exploring their unique mechanisms, applications, and implications for system performance. Introducing to HVDC transmissions, why it matters. High voltage direct current transmission plays a critical role in modern power systems, offering significant advantages over traditional alternating currents. Transmission for long distances, submarine cables, and synchronous interconnections. It minimizes transmission losses, enhances grid stability, and facilitates into integration of renewable energy sources located far from load centers. Understanding its control mechanisms is key to optimizing its performance and reliability. Understanding converter stations, the heart of HVDC. At the core of any HVDC system and converter stations, which are responsible for converting AC power to DC for transmissions and then back to AC at the receiving end. The stations utilize semiconductors devices, typically thyristors, arranged in the bridge configurations. This precise control of these devices, known as firing, determines the voltage and current waveforms, directly impacting the efficiency, stability, and power quality of the entire HVDC link. The firing control schemes are thus paramount to the system's operations. Individual phase control IPC principles and operations. Individual phase control is the fundamental firing scheme where each resistor in the converter bridge is triggered independently based on its respective AC phase voltage. In this method, the firing instant of each resistor is determined by comparing a control voltage with a ramp function derived from the commutating voltage of that specific phase. This allows for individual adjustment of the firing angle for each value, providing a high degree of flexibility in controlling the converter's output while offering precious control over individual phases. It can sometimes lead to imbalance if not carefully managed. Advantages and disadvantages of IPC. Advantages of individual phase control. Greater flexibility in controlling individual phases, allowing for dynamic adjustments. Effective in mitigations commutation failures by adjusting specific firing angles. Can be beneficial in systems with inherent AC voltage unbalances. Offers fine-tuned control over the converter operational under varying grid conditions. Disadvantages of IPC. Increased complexity in control circuitry due to independent firing of each thyristor. Potential for generation of subharmonic and uncharacterized harmonic if not perfectly balanced. Requires more sophisticated protection schemes to prevent communication overlap issues. Can lead to higher losses and reduced power quality if not preciously synchronized. Equivalent firing control principles and operations. Equivalent firing control, also known as constant firing angle control, is another primary firing scheme where the firing pulse are generated with a fixed time interval between successive firing across the converter bridge. This means that the firing instances are equally spaced over a cycle, ensuring a more symmetrical operation of the converter. This control system adjusts a single converter voltage to vary the common firing angle for all thyristors, thus simplifying the control logic. Equidistant firing control inherently promotes balanced operation and reduced harmonic destruction compared to IPC. Once again, I repeat. Equidistant firing control principles and operations. Equidistant firing control, also known as constant firing angle control, is another primary firing scheme where the firing pulses are generated with a fixed time interval between successive firing across the converter bridge. This means that the firing instances are equally spaced over a cycle, ensuring a more symmetrical operation of the converter. This control system adjusts a single control voltage to vary the common firing angle for all thyristors, thus simplifying the control logic. Equidistant firing control inherently promotes balanced operations and reduces harmonic destruction compared to IPC. Advantages and disadvantages of equidistant firing control. Advantages of EFC. Simpler control implementation due to a single control signal for all thyristors. Inherently produce a more balanced and symmetrical AC current waveforms. Reduce the generation of uncharacteristic harmonics, improving power quality. More robust against minor disturbances and less prone to communicate failures. Disadvantages of EFC. Less flexibility in compensating for individual phases, voltage imbalances. Can be less effective in preventing commutations failures in highly destroyed AC systems. Limited ability to dynamically adjust to rapid changes in grid conditions. May require external compensation for reactive power variations, especially at lower firing angles. Once again, I repeat advantages and disadvantages of EFC, equidistant firing control. Advantages of EFC: similar control implementation due to a single control signal for all thyristors inherently produces a more balanced and symmetrical AC current waveforms, reduces the generation of uncharacteristic harmonics, improving power quality, more robust against minor disturbances and less prone to commutation failures. Disadvantage of EFC: less flexibility in compensating for individual phase voltage unbalances, can be less effective in preventively communicate failures in highly destroyed AC systems, limited ability to adjust to rapid changes in grid conditions, may require external compensation for reactive power variations, especially to lower firing angles. Comparative analysis: IPC versus EFC performance metrics. Control complexity: higher individual control for each thyristor, lower common control for all thyristors. Harmonic content: higher uncharacteristic harmonics possible if not balanced, lower uncharacteristic harmonics, more symmetrical waveforms. Response to AC unbalance: better, can compensate to individual phases, limited, less able to compensate individual phases. Communicate failure preventions: more effective due to individual phase adjustments, less effective, reliefs and overall system stability. System stability can be more susceptible to instability if poorly turned, generally more stable under various operating conditions. This table summarizes the key distinctions between IPC and EFC, highlighting their different impacts on operational accepts and overall system performances. Practical applications and choosing the right control schemes. This choice between IPC and EFC largely depends on the specific requirements of the HVDC project. IPC is often performed in situations where detailed control over individual phases is crucial, such as in grids with significant AC voltage imbalances or where precise harmonic mitigations on a pre-phase basic is necessary. EFC, on the other hand, is favored for its simplicity, inherent balance, and improvement power quality characteristics, making it suitable for standard HVDC links where system stability and reduced harmonic destruction are paramount. Modern HVDC systems often employ hybrid control strategies, combining aspects of both IPC and EFC to leverage their respective strengths and optimize performance under diverse operating conditions. Conclusion and future trends of HVDC control. Both individual phase control and equidistant phase firing control are foundations to HVDC converters operations, each offering distinct advantages and disadvantages. IPC provides flexibility and individual phase compensation, while EFC ensures balanced operations and reduced harmonic distractions. This ongoing evolution of HVDC technology is driven by increasing demands for efficiency, reliability, and grid integrations of renewables. Future trends of HVDC control are moving towards more advanced, adaptive, and intelligent control schemes, often integrating artificial intelligence and machine learning. These innovations aim to achieve optimal performance, enhanced fault right through capabilities, and seamless interactions with complex modern power grids, transcending the limitations of traditional firing control methods. Thank you.